Okay. Yeah, hi. So I'm Alex. Thank you guys so much for the invitation. It's really sort of an honor to come back to my graduate university to give a talk. So anytime I get that opportunity, it's obviously really great. Yeah, so as Wojtek said, I'm going to be talking about sort of a few problems that I've been working on recently that are all surrounding this idea of how to get nonlinear representations of your data without having to build, kernels and distance matrices and things like this, but with still, provable guarantees. So I just sort of have the quick collaborator slide of everyone that, has been working on various aspects of this work. In particular, a lot of the people that have been driving a lot of this work are Caroline Moosmuller up here, Jinji Zhang for one of the problems, and Andreas down here. And I just want to give a shout out that Caroline is a postdoc that's been working with me that's actually going to be going to University of North Carolina in the fall. So pretty happy about that. Okay, so also, yeah, as Wojtek said, feel free to stop me if you have any questions. And also, I'm just going to give you, I'd say, a quick not apology, but warning. This is actually the first time that I've given this version of this talk. So if it's a little rough on the edges, I apologize. But yeah, I wanted to try something new, give some, talk about some new stuff. So, all right, what is the setting that I'm thinking about here? So I want to think about just a class of problems where you have an issue where, storing your data points is going to be expensive. Maybe you can't store everything on a single computer. You can't load everything into memory, right? And so because of this winds up producing a lot of challenges you wouldn't normally think about if just approaching, if just working on sort of general, math problems. So various settings that this will be relevant that I'll kind of talk about here will be problems involving streaming data. So this is data coming in really quick. You have to make something decision with it, throw it away, can't do much computation. This will be an example. I'm going to be talking about some statistical distances where basically you have, data sets distributed in different places, and we want to be able to compare a bunch of different data sets without having to load all pairs in order to do the, n squared comparisons or something. And then also I'm going to talk about some quantization problems that we've been working on recently, where you want to really make sure that your data is going to be able to be compressed down to some, binary string or something like this for efficient storage and future computation. So that's kind of the setting, and I'll talk about some, the applications and also just kind of why this is a set of interesting math problems to me. So I come from sort of a manifold learning background. That's what I worked on when I was at Maryland. And a lot of manifold learning, you have this situation where you need to work on kernels, which are giving you pairwise similarity, or you have to work on distance matrices or something like that, right? And again, not only is this an n by n matrix that's expensive to compute, but it's made even worse if loading pairs is, much more expensive than just random access memory, okay? So, this is sort of the reason that I got interested in some of this, is how to avoid some of those computational bottlenecks. Maybe some of you, if you're familiar with kernel methods, are familiar with random feature models, which are ways to avoid that pairwise computation, but random features still require floating point storage, which is something we're going to kind of discuss in this talk. When you're computing statistical distances, you have to load pairs of data sets. It's obviously expensive as well. And so I wanted to, just kind of give why I got interested in this, which is that, I work some on deep learning, which I'm not going to talk in this talk about deep learning at all. But one of the things that I've really taken away from deep learning as being really important is the ability to work on batched data. Load in a little bit, do something, load in a little bit more, do something else, really keep your model updating such that you didn't need to have everything in memory at the same time. I think that's one of the real strengths of the neural network, and that's something that we're looking to exploit in all of the examples and algorithms we're working on. Yeah, so that's basically, the overview and the connecting thing. I'm going to talk about a few topics here. So the first is going to have to do with building features of not just points, but actually of distributions or point clouds, such that we can quickly approximate Wasserstein distances, and also do classification on said point clouds or distributions. I'm also going to be talking about building binarized representations of reproducing kernel Hilbert spaces. So this kind of gets into this idea of like data sketching, but also quantizing at the same time. And then some, if I have the time, some work that we've been doing, some more applied work on sort of streaming data and using boosted kernel regression. So that's the overview. Okay, so I'm gonna go ahead and jump into the first problem, talking about optimal transport, specifically what's called linearized optimal transport. So what is the question or the set of questions that we're trying to address here? Okay, so this is going to be a little bit of a different setting than you're normally used to thinking about in machine learning. We're not dealing with some points in some vector space, but instead our data in this case is actually going to be an entire distribution. Okay, so instead of having n data points sampled from one distribution, you actually have n distributions. You sample point clouds from each one. Okay, and those distributions are going to have labels on them. So I'll give a couple examples in just a second of where this is actually quite relevant. But then the question we have is, how do you build a classifier on that? That's one question, right? I want to figure out how to label these distributions. So this is going to require some assumptions on the function, you know, the classes and how we define classes and stuff. But there's a second question that's motivated here, which is, what is the metric that we're computing if we build some nice set of features for a distribution, right? Because if you want to use any off-the-shelf classifier, what do you have to do? You have to take a distribution, embed it into a Hilbert space or something easy that you can work with. And so the question is, what's the geometry we're inducing there by creating some set of features and then just considering a natural distance in that space, okay? So these are kind of the main questions motivating this. And I just want to mention that the goal of a distance metric between distributions, sort of what's the natural distance metric between distributions? Well, that would be to use optimal transport, right? So this is sort of a natural way to think about how to define distances between two distributions. You know, the basic, if you've never seen optimal transport before, the basic idea is, how do you, what is the minimal amount of work it's going to take you to move some, you know, some mountain of sand into, you know, a hole of similar volume, right? So this is the basic idea. We can be a little bit more precise with that of what are we considering here. So we're going to be talking about Wasserstein 2 distances. Okay. And so if you're considering the Wasserstein 2 distance between two distributions, what is this? Well, it's, as I said, minimal work, right? So I'm writing a version of optimal transport. This is not, I'm not going to go too much into, you know, the every single possible, you know, Cantor-Vorch duality and all this stuff. But basically, we're just going to assume that we have some transport function, transport map that we can find. And what we're saying is, of all the possible transport maps that would take distribution mu to distribution nu, we want to find the one that took the minimal work. And again, work here is considered over the distance squared, right? So that's how much it costs to move one piece of sand from here to there. Okay. All right, so that's the distance, but we're actually going to be focusing a little bit more on the map itself. So it winds up that the optimal transport map, the one that attains the argmin, has some really useful properties that we'll be able to exploit. And I should note that, again, there's not always a function that does this. Sometimes you can have a coupling. I'm not going to focus on that too much in this talk. We are doing some recent work that's extending a lot of what I talk about to couplings. But for now, we're just going to think about, you know, the existence of there being a transport map function. Okay. All right, so optimal transport, a lot of benefits, incorporates the sort of natural geometry of your space. There's a well-studied theory of this, obviously. A huge con is obviously that computing this map is very slow. There are ways to speed this up, but for the context of loading in a bunch of data points and wanting to do everything in a single pass, I just want to point out that it's really, if you have n distributions and you want to compute, say, all pairwise distances, that's insanely expensive because each Wasserstein distance that you have to compute requires some optimization scheme. And if you're trying to compute all pairwise distances, that's now n squared expensive computations, which we don't want to do. We want to avoid that. Okay. And also, I just want to point out that another sort of big issue is, I said one of the questions I was interested in was how to do classification. Well, distance matrices don't necessarily lend themselves to how to build a nice off-the-shelf classifier. So, that's sort of motivating what I'm going to talk about right now. All right, so I'm going to propose an alternative for dealing with a bunch of different distributions and trying to build features of them and trying to compute distances between them, okay? And this is what's called the LOT embedding. This did not originally come from me. This is Gustavo Rode worked on some of this. There's been a number of others. Akram Al-Drubi works on this recently. He actually spoke about some things related to this in one dimension at the John's 80th Jubilee a couple of years ago, right before COVID. Okay, so in fact, actually, that's the first place I found out about it, to be honest. All right, so what's the idea? So I'm going to embed my distribution into an L2 space. So how am I going to do that? Well, I'm going to take a fixed reference distribution, okay? And that reference distribution, for the moment, I'm going to say it can be anything, okay? So it's just a Gaussian or something. And what I'm going to do is I'm going to compute the optimal transport map that takes me from my reference distribution to one of my data sets, okay? And I'm now going to encode that data set, that distribution, by the transport map, okay? So the way you can think about this is if I have n distributions, I have to compute n transport maps. It's like spokes on a wheel coming out, going to all of these different distributions, okay? And I claim that using this map as a feature space is actually going to be very, very, very useful for downstream tasks. Okay, that's the idea. So what are the tasks that we could do? Well, one would be to do some sort of learning algorithm. So if I wanted to build a classifier on distributions, what I could do is learn a function that takes me from this L2 space to, whatever labels or regression or whatever that I want to do. Another thing I could do is try to compute pairwise distances. Right? Maybe I want to do some unsupervised embedding where I try to find clusters of distributions. These distributions look similar. These distributions look similar. Well, hopefully this would actually be way cheaper to compute than all pairwise optimal transports, right? Because now what I have is I have the transport map here and the transport map here, and now I just have to compute a norm, which is quite cheap. Okay. So this leads to some questions. What do we actually need about this embedding in order to learn F? How complicated does this classifier have to be? What are natural clusters that we're going to be able to, natural data sets that we'll be able to classify? What does this distance do? And how is it related to the actual optimal transport? These kinds of things. Okay. So I always give a shout out to this whenever I talk about this LOT work. So actually within the same week that Caroline and I put up a paper, the first paper that we wrote about LOT, Akram Al-Drubi and Gustavo Rode put out a similar paper. So we kind of have concurrent stuff going on. Different theory and scope. So I'm not, stepping on each other's there, but we're sort of both working on a lot of this stuff concurrently and discussing and collaborating on some of it as well since that point. So, all right. So what I want to talk about is just kind of answering the basic question of, okay, can I, if I'm doing this, am I going to be able to build classifiers to differentiate distributions for any type of distribution for any family of distributions, or am I only going to do this for very limited circumstances, right? It's kind of the question. Well, to motivate, to address that question, I have to set up a little bit of notation. So heuristically, what I want to do here is I want to find families of group actions that sort of behave nicely with optimal transport. Okay, and when I say group action, what I mean is, well, say you had a distribution, you can do things to that distribution. You can shift it, you can scale it, you can perturb it, you can shear it, you can do all kinds of things, right? Which of those interacts nicely with optimal transport? Which of them don't, right? And these are going to be what we're going to call compatible transformations, okay? So first off, I should note, it's easy to show that if you had some push forward on a transport map, that's the same as doing the push forward on the result of the transport map. Those things are always going to be equal to each other. Well, almost always going to be equal to each other. The problem is, when is this thing on the left the optimal transport map? Okay. So what I'm saying here is we kind of have this, commutativity diagram. I could go from sigma, my reference distribution, and I could take my optimal map to get to mu, and then I could shift mu or scale mu or perturb mu in some way. Or I could have worked with that shifted, scaled, perturbed mu and computed the optimal transport maps directly from sigma to there. Okay. And the whole problem of talking about linearized optimal transport is actually going to boil down to when is this actually the optimal transport map or close to the optimal transport map? Okay. So as I said, I have to define a couple of terms. Okay. So the first is we're going to talk about what's called a compatible set of transformations. So say you have this F sigma. This is my LOT embedding. It's an optimal transport map, maybe renormalized or rescaled or something, but the idea is, okay, if I were to do some operation in mu and then take LOT embedding, or if I were to take the LOT embedding of mu and then do something to it, when are these things effectively, the same? Okay. So this would be, anything that satisfies this would be what's called a compatible transformation. And examples of compatible transformations are actually shifts and scalings, and combinations, just shifts and scalings. Okay. So what I mean by that is if I wanted to map from sigma to mu and then shift to mu, right? The optimal transport way to get, it's like that's sort of the optimal route to get there. And you could have done the same thing by finding the optimal transport from sigma to the shifted version of mu. They're sort of the same map. Okay. And you get some nice properties about this that sort of, if you have a compatible transformation, you preserve things like convexity. If you had a convex set of compatible transformations, then if you do the LOT embedding of all these things, that resulting set in this L2 space is also going to be convex. Okay. I won't go into proof of that, but this is actually not too hard to prove. Okay. Similarly, I can have something that we call an almost compatible map. So almost compatible map means I almost have this relationship. And when you have an almost compatible map, you wind up getting that if you were dealing with a set of convex push forwards, the resulting LOT embedding is not exactly a convex set, but there's a tube around it such that it is there, you would have convexity. Okay. And examples of that would be sort of slight perturbations and things like this of a distribution. Okay. So, this is kind of going to be our family of actions we can do to a distribution. Okay. We can shift distributions, we can scale distributions, we can perturb distributions. Okay, that's going to be all a family of stuff that we can do. And I want to talk about what happens if I do these things to a distribution, right? Obviously, I'm not really changing it too much. So, if you think about having a bunch of training data, which is like a bunch of shifted versions of the same distribution, hopefully I should be able to classify them all as basically being the same. Okay. Okay. So what can we actually say here? Well, I'll just go ahead and jump to the chase, which is that we actually have some pretty nice results, which is that assume that your reference distribution, that thing that we're comparing every object to, is absolutely continuous. Okay. And assume we have a bunch of almost compatible transformations of some distribution mu, right? So say mu is, a uniform distribution in some dimension, right? I haven't mentioned anything about dimension. These can be in D dimensions, right? I have a bunch of shifts and scalings and perturbations of it, the uniform distribution on some, shape. And then I have some other distribution, nu, Gaussian, I don't know, whatever. And I have a bunch of shifts and scalings and stuff like that. Well, I want to be able to address the question and ask, okay, can I classify the difference between all of these news and actions I've done to them and all of these mews and actions I've done to them? Okay. And what we can wind up saying is actually pretty nice, which is that basically, if I had all of my shift, scalings, perturbations, and mu, all my shift, scalings, and perturbations and nu, and these sets are compact, so basically I wasn't pushing things out to infinity. And the actual distributions, those sets had some minimal separation in Wasserstein distance. Then it winds up when I do this LOT embedding, those two sets are actually going to be linearly separable. Okay, not just separate, not just that they're disjoint, but they're going to be linearly separable, which means I can build a linear classifier to tell the difference between these two families. Okay. And by the way, I should note, we can, if we're talking about, this is just for delta compatible and compatible. If we're talking about actually shifts and scalings and like really focusing on particular actions, we can characterize exactly what these constants are. Okay. But so I want to step back and think about that for a second. It's pretty nice, right? So what does that mean? All right, so you had a bunch of distributions, right? Maybe they're on different computers. For each one, I just need to figure out, how do I deform a Gaussian to look like that distribution? How do I deform a Gaussian to look like that distribution, right? Those are my features. And now, what we can basically say here is, if I had a bunch of distributions that kind of look like mu, a bunch of distributions that kind of look like nu, once I communicate the features, I can build a linear classifier to differentiate. Okay. And oh, sorry, I see something in the chat. Oh, somebody was just asking a quick question about the star. Yeah, sorry. I did not define the star. I apologize. Basically, what that is take every push forward that exists in that set H and apply it to mu. Okay, so if this is a bunch of shifts, it's basically just shifting mu to a bunch of different places. Okay. All right. So similarly, that's sort of the supervised problem. We can talk about the unsupervised problem. So we had this W2 LOT, which is basically just the distance between the transport plans, right? That is relatively, let's say, cheap to compute, right? Or we could have computed all pairwise Wasserstein distances, okay? So say that the distributions we're working with are all these shifts, scalings, perturbations of tau, some distribution. Then it winds up that the LOT distance and the actual Wasserstein distance between these sets of distributions, they're almost isometric. And if we only work with compatible transformations, shifts, scalings, then it is an isometry, right? Cheap distance, expensive distance will be an isometry to each other. And if you allow more transformations such as perturbations, then it winds up that you are almost isometry, and specifically Halder 1/2 in how much you perturb. Okay. So again, if we're thinking about this from a computational perspective, this is really nice, because now instead of having to pick up each distribution from each computer and do the Wasserstein comparison, do all, n squared optimal transport calculations. Now I just need to do n of them and then compute just some Hilbert norms, and I can get something that's almost the same set of distances. Okay. Yeah, so, oh, I should note also, we can remove the need to have our tau. I probably wrote this a little awkward in the way that I did it. I can remove the need for our tau to be absolutely continuous, and you can still have something that's Halder continuous, just hurts the Halder constant a little bit. I won't go into the details of it. If you're interested in optimal transport, it has to do with these, what are they called? Caffarelli regularity conditions, right? If you remove them, you can still establish some pretty nice results, just with a worse Holder constant. Okay. And then there's some additional work that we've done that is sort of shown that there are actually more sets of compatible transformations than just shifts and scalings. Okay. Shifts and scalings are compatible transformations if you make no assumptions about your reference distribution or about your data. Just, you know, it's sort of a, you just sort of say like, all right, I just want to be able to do this sort of black box off the shelf thing. Okay. If we make a little bit more of an assumption, and I'll show in a minute where this is relevant, but let's say we make an assumption that our reference distribution is an example of a mu, right? Then we can actually characterize more possible compatible transformations. And specifically, it comes down to this idea of I will now be able to shear, and there are certain directions I'll be able to shear in. And it has to do with the Jacobian of the map between sigma and mu. Okay. But what this means is that now compatible transformations of some mu would be shifts and scalings, and also shearings, okay, along certain principal axes. Okay. Right. So what this motivates is that we could even propose an additional sort of augmentation of this whole LOT framework that I've described, which is, what if we didn't just have one reference distribution, right? Say I had a mu and all its transformations, nu and all of its transformations. Well, then what I could do is build sort of two LOT embeddings. One is that I pick an element of mu, right? That looks like a mu, and I use that as my reference distribution. And another is that I pick an element that kind of looks like nu, and I use that as its reference distribution. And then I just concatenate these LOT embeddings. And then I build a classifier. Okay. And it winds up that we can basically use all the equivalent theory that I've just described to say that you can still just build something that's a linear separator. And you still have these near isometries and all this other stuff. Okay. So I know I've sort of jumped into the math of the optimal transport and all of this. I want to step back for a second. I want to think about the actual applications, and I want to think a little bit about what this means in terms of the actual computation. Okay. So what is the relevance in the experimental setting? Well, again, what we're saying is if I had all of these transformations of some mu, and I'm assuming that any one of these compatible transformations of mu sort of keeps it within class, right? I get the same classifier or the same label. Then what we're saying is that we could create a linear classifier between the transformations of mu and the transformations of mu. Okay. So again, what I have not talked about up to this point is these are L2 spaces. So that's still, classifiers in some function space, right? But it winds up that we can actually downsample this pretty easily to be into some finite dimensional space that can actually be seen as a type of perturbation and still have nice guarantees about separability. And I should also note that if the whole goal is to preserve pairwise distances, we could do some sort of JL embedding and maintain all of the pairwise distances while vastly reducing the dimension. Okay. So let's kind of talk about how this actually works in practice. Actually, so just for the sake of time, I'm going to go to the sort of most interesting problem to me. So what was kind of a motivating example of this? Well, there's this data set or this medical test that I've been quite interested in for several years now, called flow cytometry. And what flow cytometry is doctor draws your blood, treats your blood with some chemicals, drops it through this machine, one cell at a time, and gets like a 9-dimensional representation of each cell. Okay. And so a person, you had 50,000 points drawn, 50,000 cells drawn from you. Then it winds up that you are now represented as a point cloud in 9 dimensions. Okay. And what that point cloud looks like actually says a lot about whether or not you have some type of blood disease like leukemia. Okay. And I should note that these point clouds are very strange. These are not simple point clouds. Okay. This is an example of someone that's healthy. And this is an example of someone that has AML. Can you tell me what the differences are? Right? I mean, it's a little complicated. And this is only, 3D slices of that high dimensional thing. Okay. And basically what winds up happening, the simplest way that a medical doctor would actually look at this to determine if you have AML is look at all of the 2D slices and see if they can recognize that this looks like somebody that has AML. There's more advanced work that involves gating, what's called gating, but it's again on these 2-dimensional slices. So, I mean, at the end of the day, these are samples from some distribution associated to a person, and I want to classify, is this a healthy person or a sick person? Okay. So I've done some work on this related to unsupervised learning. We can, cluster people, and we did a decent job of being able to separate healthy from sick, but now I want to build an actual classifier. So let's do that. So it winds up that you can compute an LOT embedding per person. So in that case, we're using some code that basically has the reference distribution just be a uniform reference distribution on the sort of 9-dimensional cube. And that allows us to have computation go a little bit faster. There's some, benefits in code there. What that actually gives us is now, all right, we have the feature map that took us from the uniform distribution to this person, uniform distribution to this person, uniform distribution to this person, right? Stack all the, subsample them, stack them all together. Do some dimension reduction of that down to, 25 dimensions. And then fit a linear classifier. Okay, linear classifier. And what we have here is just a projection down to 2 dimensions that maintains the separability. And this is the collection of all of the healthy people. And this is the collection of all of the people that have AML. And you can see that that feature map really did have the correct information contained in it and allowed us to build this really nice classifier. And this is just a visualization, but then we can even look at things like, all right, let's say we trained our linear classifier, because it's a linear classifier, it doesn't mean that much data, on 15 examples of people that were sick and 50 examples of people that were healthy, and then tested on the rest of the data set. Okay, that's tiny amounts of data. And already, as you can see, we get fantastic classification. So this is very preliminary results. This was not actually in the original paper. This is something we're kind of pushing forward with now. But I just find this to be kind of a really nice, motivating example of why thinking about this type of problem is really interesting. And I also want to mention that this didn't even require, theoretically, this didn't, I mean, I have all this data on my computer, right? But this didn't even technically require us to have each person's flow cytometry on the same system, right? With, HIPAA servers and everything, all data is distributed everywhere. You just need to create this feature transformation on each system and just communicate the result or some dimension reduced version of the result. And then you can fit it into the classifier. Okay. So this is, an example of some work that I've been doing where we're trying to avoid having to do all these pairwise distances, right? And instead just compute features of each distribution individually. So there's a lot of current work that we're doing on this. Just to mention, again, a linear separator is very easy to compute. So we're actually finishing up some work now with my student Jinji Zhang. It's about actually incorporating active learning. So that means I want to figure out, if I'm allowed to ask for labels of particular distributions, then I can learn my classifier much, much faster. And this is really relevant in the medical context because, doctors don't have a lot of time to give me, 1,000 labeled examples. So instead, if I can just say, like, could you please label this one? Now, could you please label this one? And please label this one? Okay, now we're done. That would obviously be much better and sort of more realistic of what would actually happen if we were working on this medical problem. A downside of everything I've talked about here is that computing optimal transport is really expensive. It's still an optimization scheme. There's a lot of speed ups that involve what's called entropic regularization. So Caroline Moosmuller and I, along with our student Varun, are finishing up some work on generalizing everything that I just described to this entropic optimal transport or Sinkhorn distances, okay, which are much faster. Okay, so this is some work. If it's all right, and if there are questions, please let me know. Otherwise, I can kind of go on to another example of some work we've been doing recently. Okay. So I'm going to talk about next sort of set of problems that we're thinking about. So now I'm going to return to a little bit more straightforward scenario where you just have data points in a vector space or something. So normally one would, if you wanted to do some nonlinear dimension reduction or do some, nonlinear regression, one would want to learn a kernel, right? So pairwise similarity between all of your points. Once you have that kernel matrix on your training data, you can do kernel regression. You can do, pick your favorite dimension reduction tool, blah, blah, blah. Obviously, that requires me to load in all pairs of points. I don't want to do that. Okay. Now, there are ways to get around that, which I'll mention in just a second. But the main question we want to ask here is, I don't even want to just do it where I only pass through my data point once to find a representation. I don't want to, but also I want to not just store a representation as floats, but actually figure out a coarsely quantized representation, or in this case, even a binary representation of my data point. Okay. So that's the goal. The question is, can I find a binary representation of a data point such that when I take inner products or some weighted inner product between those representations, I'm actually approximating my kernel? Okay, because if I can, then I've found a quantized version of the feature space of that kernel. And once it's quantized, I can do 1-bit calculations, I can do 1-bit storage, everything becomes a lot nicer. Okay. So this is some work I've been doing with my student, Jinji Zhang, who is co-advised by and also worked on this project, Rayan Saab. So this is some work between the three of us. Yeah, and that's kind of, the motivating question, right? So for those of you that are familiar with kernel methods, maybe you're not surprised that there's a way to figure out an embedding using a single pass of your data. This is what's called pretty well known at this point, random Fourier features by Ben Recht and Rahimi. So what's the basic idea to it? Say you have a kernel that is translation invariant. If it's translation invariant, then you can use this thing called Bachner's theorem that basically says it can be represented as the expected value in the frequency space of, e to the I, some frequency vector inner product with x. Okay. So basically what you're doing is you're hitting your data point with a bunch of random features. You're taking the complex exponential of those features, and that is now your representation. And if you take inner products between the representation of x and the representation of y, that inner product is going to be very similar to KS1. Okay, and we can be precise about that. What is the distribution you're sampling from? How many samples do you need? Everything I've described here converges like 1 over square root of m, where m is the number of random vectors that you apply. And also this is complex, but you can do a real version of it as well. Right? So that would be a way to go through your data in a single pass and get some nice feature space representation. But again, this representation is a floating point. Okay. So what we want to do is say, all right, can we quantize this? Can this actually be quantized all the way down to some binary embedding or very, very low bit embedding, right? And when we do that quantization, will we still have a guarantee on the inner product? And I should note there are for certain kernels, there exist some quantization methods. What we're doing is pretty much independent of the kernel. All we need is just the original assumptions that it's translation invariant. Okay. All right. So that's one ingredient to this problem. What's the other ingredient to this problem? Well, the other ingredient is noise shaping quantizers, or what we'll talk about in a minute, which is the sigma delta quantization. Okay. So, well, actually, before I mention this, I should just kind of comment. Maybe the first thing that you think is, oh, I have a vector of a bunch of floating points. Maybe I just want to quantize them by doing some, MSQ. Just flip if it's positive, it's a 1. If it's negative, it's a -1, and just do that to every single point. Maybe I don't have to convince any of you. I think in the FFT talk, maybe it's a well-known idea, but that's not a good way to quantize. That's not going to be stable, and it's not going to preserve any sort of inner product structure that we want. So what instead I want to talk about is what is a stable quantization, a stable noise shaper quantization. Well, basically what it is it's a quantization where you're able to project your data down to some alphabet of the same size. And this alphabet is just plus minus ones, or whatever size alphabet you want. It's stable if there exists a lower triangular matrix such that you can get back to what your original vector was, right? And if your vector being bounded means that this sort of tracking of the error is also bounded. Okay. So, this is the basic idea, and this motivated sigma delta quantization, right? So there's different types of quantizers you could do. In this case, what we're doing is we're saying, all right, the first way you could quantize would just be to flip everything to the closest element of your alphabet. Are you close to a 1 or a -1? But then for a first order sigma delta scheme, what you're doing is you're saying, all right, I'm going to quantize my first entry. Now I'm going to keep track of how much error that induced and incorporate that when quantizing my next entry. And I'm going to keep track of the error and then quantize again, and then keep track of the error and quantize again. And it's first order because we're basically looking 1 back in this scheme. Second order would mean we looked 2 back. Rth order, you look R back. Okay. And this actually, is a stable quantization scheme. Okay. So with that, we can even describe exactly what that triangular matrix is. And we're going to use that in a moment. Okay. So along with noise shaping quantizers, another thing that I should bring up is what is the actual metric we're going to put on this quantization? Well, what we're going to use is an inner product that's weighted by some V. And this V has a very, very particular form. And it's equivalent to saying that we apply V to Q, apply V to Q tilde. That's our inner product. So V has this very particular form that's sort of a condensation operator, sort of grouping together all of the quantized bits. So I won't go too much into this at the moment, but effectively what this is sort of a deterministic, very straightforward, very easy to implement matrix that will sort of combine all of my bits in an appropriate way and with an appropriate weighting, such that when I then take inner products, hopefully I'll be able to recover something that looked like the original code. Okay. So that's the whole setup and sort of the ingredients. So I want to talk about what we can actually do with this. Okay. All right. So the sort of first result that we can establish here, which, I'm sorry. I mentioned Jinji. I forgot to mention Harish, who somebody else has been working on parts of this problem as well. So Harish actually had worked some on the LOT stuff, and he's also been working on this kernel quantization. But what can we say here? Well, what we can say is, all right, say we had some data, compact. We had some normalized shift invariant kernel. When I say normalized, I just mean that K0, 0 is equal to 1. So, the exponential or the Gaussian, right? Perfect example. Then what we get is a series of steps that we apply the moment a point comes in, right? You get some xn, and what do? you quantize it, or you apply random Fourier features, okay, specifically M of them, and you quantize those random Fourier features using your favorite quantization scheme. For now, I'm describing sigma delta. I should note at the bottom, there are other sort of distributed noise shaping quantizers that this works with as well. But the point is that you have your random Fourier features and you quantize using sigma delta. Okay. And then you build this condensation operator that we know exactly what it looks like. And now you have a very nice quantized embedding of your data point that you computed the moment your data point came in. So the question is, does this actually reflect reality? Like, does this give us back the nice kernel? So if we define inner products in that space using this V, then what we can establish is actually pointwise with high probability, our quantized inner products and our true kernel are going to be close to each other. And specifically, it's going to be close in something that looks like 1 over square root the number of random, something related to the number of random Fourier features by this factor of lambda, plus a little bit extra that has to do with the actual quantization error. And we can actually get this to go away by playing around with this lambda parameter. Okay. So what this says is pointwise, we're actually in pretty good shape. Kx, y, inner product in quantized space, the actual kernel, pretty much the same. But we can go beyond that, and we can actually also establish some spectral bounds. So similarly, what we can say is if we're given n training points, sorry, that should be the size of x is equal to n. Then, and we can't say this for everything, but right now we can say it for first order sigma delta quantization. We can actually establish that, I apologize, I have one other error here. This should be eta, not lambda. Those are two separate things. This should also be an eta. But what we can establish is that the original matrix, right? I apologize, one other tiny error that I have here. This shouldn't just be a less than or equal. This should actually be the spectral less than or equal. Basically that if you took this matrix minus this matrix, it would be positive definite. Basically, this means we're able to control the actual eigenvalues of this kernel, right? But what we get is a spectral bound that says that with high probability, the quantized kernel is going to be spectrally sort of squeezed between the original kernel and some other factor of the original kernel with some high probability. And we can get exact bounds on that probability in terms of the number of features that we keep, in terms of how tightly we want to nail nail this kernel spectrally, you know, and everything works out. Okay. Yeah, so that sort of is what we want, right? That when you quantize, you still have something that looks like the feature space it's supposed to look like, right? And so then we can actually use this. Oh, sorry, before I do, one other comment, which is the spatial complexity of this. So this is just a comparison to several different other ways of doing it. If you had random Fourier features and you were storing, you know, single float, then you'd have 32 times the number of random Fourier features. That's how many bits it would take to store your data. There's this idea of what's called semi-quantization. You quantize one side of the inner product, but not the other. There's another approach called stochastic quantization that I do really like, and it actually does quantize quite nicely. But the problem is that the embedding is not deterministic with respect to the data point x. So what that means is if I fed in x one time, I could get one binary vector. And if I fed in x the next time, I could get a different binary vector, which is kind of not what you want, right? So we're actually trying to build something that's deterministic, feed in an x, it's going to go to the same binary vector every time. And what we wind up getting is storage capacity up to this, which is, you know, quite small, and B is the number of bits that we wanted. So if we wanted 1 bit quantization, B is, you know, 1. Okay. Yeah, so cool. We have a quantized space what can we do with that quantized space? Well, what we can do is we can actually run basic kernel methods that you would want in the quantized space, right? So I just kind of have a couple of examples here, and we're actually looking to build this out into more sort of robust applications. But just sort of as a demonstration for the moment, what I'm going to do is take some data from, some dimension 5 object, say, take some fairly complicated function of that data. Okay. This function is something that's used in several of the kernel quantization, several papers in the kernel quantization literature, which is why we used it here. And what we see is that if we compare to the number of random features that we keep, we're doing quite well. But if we especially compare to the accuracy as a function of the number of bits of storage, we see that for this kernel ridge regression, we're doing fantastic and even better than the stochastic quantization. And again, we still have this deterministic aspect, which is the plus. Similarly, one could do this for building a kernel SVM, right? You could have some complicated kernel SVM, or you could just build a linear SVM in the feature space. We have some examples here on just sort of a simple handwritten digit data set. It's even simpler than MNIST, pretty small. But we wind up seeing again that for, first order sigma delta, second order sigma delta, and then this beta is the distributed noise shaping that I referred to briefly. We do quite well, and actually almost as well as the random Fourier features themselves. And similarly, in terms of the amount of bits we needed to store all of our data, we're beating the stochastic quantization. Another thing you could do in a kernel feature space is maximum mean discrepancy. So kernel maximum mean discrepancy is like a 2-sample test. Did these points come from the same distribution or different distributions? The easiest way to compute this, if all things being equal, would be to look in the feature space of the kernel and compute the mean of one data set and compute the mean of the other data set and just say, are those means the same or not the same? Okay. And there's ways to compute the power of this test using what's called a permutation test. I won't go into the details of that. My point here is to say that once again, what we get is with this quantized feature space, we're actually doing exceedingly well and not really losing anything in terms of the downstream tasks, but we're still getting pretty efficient storage of the data. Okay. So unfortunately, I think I ran a little long, so I am not going to have a chance to get to the last example, which is about boosted streaming data kernel regression. If you're interested, I will skip the details, but instead just come to the list of some of the papers associated. So for the LOT work that I was talking about for distributions, we have the work with Caroline, and then the work that's also with Varun and Harish. These are both come out in the last, I know this says 2020, but in reality, we basically put it up in 2021. The sigma delta and distributed quantization, 2021. And then for the streaming boosted kernel regression, if you're interested in this, this is some work with Yoav Freund and a student I work with, Andreas, that actually just got published in Applied Math and Computation. So code available. Yeah, so this is a little bit of what's going on in my group.